In chapter 22, we're going to look at basically two types of reactions. We're going to look at alpha substitution reactions, and then we're going to look at carbonyl condensation reactions. So let's just talk about each one of these types of reactions momentarily. If we look at an alpha substitution reaction, what happens in an alpha substitution reaction is that a hydrogen on the alpha carbon, the alpha to the carbonyl, is replaced with something else. The way this reaction occurs is that a base comes in and pulls off that hydrogen. Now, normally that hydrogen is not very acidic, but if we look at what happens when that hydrogen leaves, remember it leaves its electron pair behind, this structure is resonance stabilized. So therefore that hydrogen is a little more acidic than what we would normally expect. Then an electrophile comes in and attacks the carbon and adds to the carbon. So the overall result is that the hydrogen is replaced with the electrophile. Now the second type of reaction is a carbonyl condensation reaction. And what basically happens is two compounds containing carbonyl groups, remember the carbonyl group is the C double bond O, combine together. So what happens is the first step is the same. The base comes in and pulls off one of the alpha hydrogens. But instead of having an electrophile present, this species now acts as a nucleophile, and it can attack another C double bond O. And remember, nucleophiles attack the C double bond O at the carbon, kicking out that pair of electrons. So what we end up with is the pair of electrons, and I haven't shown my electrons on my oxygen here, is on the oxygen, and therefore it's a negative charge. Then we add an alcohol or some kind of other compound that has an acidic hydrogen in it, and we protonate that oxygen. So the overall result is that the reaction combines two C double bond O compounds. So for example, we can also do this with esters. Notice we form the negative charged nucleophile by again removing an alpha hydrogen. When this comes in and attacks, the C double bond O goes up, and we end up with this species. We end up with this species because the C double bond goes up and then comes back down, kicking off the OR group. We'll look at these reactions in greater detail as we go on, but this is just a general overview of what happens in these reactions. So now we're going to talk about something that's really important in understanding the chemistry that goes on here. And that's something called keto-enol tautomerism. We've seen this before back in chapters 8 and 9 when we were dealing with the C double bond C's and C triple bond C's. But let's just take this compound and pull a hydrogen off using a base. Again, we said that we have this resonance structure form. Again, this resonance structure is basically where this pair of electrons comes down and the pair of electrons on the double bond go up to the oxygen. This is called the keto form because it contains a keto group. This is called the enol form because it contains an oxygen attached to the C double bond C. Now, if we protonate this, notice we can protonate the oxygen in the enol form to get this enol, or we can protonate the keto form and get the ketone. Now listen carefully. Normally the keto form is the more dominant species in neutral solutions. But if it's a negative species, the enol form is the more stable one. It's actually, if you deprotonate it, the enol is more stable than the keto. And that makes sense because notice that the negative charge is on the oxygen versus being on the carbon. So we're going to look at how that interacts in just a little bit. So we can take a ketone or a carbonyl compound and we can protonate it. Notice when we protonate it, the oxygen gets protonated. And then we can take the water off, and we can take the water and use it to pull a hydrogen off to give us the enol form. So notice this occurs in both acidic and basic solution, this keto-enol tautomerism. One of the effects of this is the destruction of chiral centers. If I asked you, was this compound chiral? You would say, yes, it is chiral because this carbon has 4 different groups attached to it. But notice it has a hydrogen on that alpha carbon that is chiral. So if we were to just add a small amount of acid or base to this compound, it would destroy the chirality of that. Because remember what happens, this H gets pulled off, and when it gets put back on later on, it may or may not go to the same side. So therefore, whenever we have something that has an alpha hydrogen in the, or a hydrogen in the alpha position, and that carbon happens to be chiral, that chirality is easily lost, either in acidic or basic solution. Now, we said that that hydrogen was more acidic than normal. Let's just look at a table that illustrates that. We know that the hydrogen attached to a C double bond C has a pKa of about 40. It's very non-acidic. The triple bond, remember, is more acidic because of the sp hybridized bond versus the sp2 hybridized bond. But notice it still has a pKa of 25. Even though this hydrogen is on an sp3 hybridized carbon, its pKa is 20 because of the resonance structures that we talked about earlier. But it's not as acidic as alcohols, nor as acidic as water, okay? So what we can say about that hydrogen is it's less acidic than alcohol and water, but more acidic than normal carbons or normal carbon-hydrogen bonds. Now, this section always confuses students, and there's no reason to be confused here. We're going to talk about a compound called LDA. Before we talk about it, I want to go back to the reactions that I looked at earlier. In these reactions, whenever we added a base, this was a very good equilibrium. And the equilibrium could lie to the right or to the left. Using LDA, we shift that equilibrium. So let's go back now to page 4 and look at what LDA does. LDA is just a compound. It's called lithium diisopropyl amine. And the way you make that compound is you take diisopropyl amine and treat it with this lithium reagent. The lithium and the hydrogen trade places. So now we have a salt, an ionic compound. Notice the nitrogen is a negative charge. So the nitrogen is going to be our base. A negatively charged nitrogen is a very good base. Also notice that the 2 isopropyl groups are very large. Therefore, this compound does not act very easily as a nucleophile because of the bulkiness of it. But it will be a very, very good base. So what happens when we add LDA to this reaction is whenever it pulls off this alpha hydrogen, it traps the equilibrium far to the right because this compound is very non-acidic. It's got a very large pKa. So therefore, the equilibrium lies very strongly to the right. So all we're saying on this page is that we can use LDA instead of OH minus to shift the equilibrium to the right. It's a very strong base. but since it's very bulky, it's a very weak nucleophile. And that makes it perfect for this reaction. So now let's look at a reaction. Let's look at what's called alpha halogenation of ketones. Now, just as the name implies, alpha halogenation of ketones replaces one of the hydrogens in the alpha position with a halogen. So what happens is the OH comes in and pulls off a hydrogen. And that hydrogen gets replaced with a halogen because this now negatively charged species comes out, attacks the halogen, kicking off the other halogen. So what ends up happening is we get alpha halogenation. If we were to use a compound that had two hydrogens, we would get alpha halogenation twice, as long as we have an excess of the halogen. So basically the same thing occurs twice. If there's three hydrogens on there, though, this reaction is a little bit different. Let me explain what happens when you have three hydrogens on the same carbon. The reaction occurs three times, so we get trihalogenation. But the reaction does not stop there. This OH comes in and attacks the C double bond O, kicking this group off. Then this group pulls off the acidic hydrogen, and you end up with what's called haloform. Okay, if this were a chlorine, it would be chloroform. If it were an iodine, it would be iodoform. So, if you have a question on the test and you have a methyl ketone, notice this is called a methyl ketone because it's a methyl group attached to the C double bond O, and you add halogens to it in the presence of base, it does not stop at this step. It continues on to give you the unprotonated form of the carboxylic acid and the haloform compound. Now, if the halogen happens to be iodine, this is a very, very good test for methyl ketones because it forms iodoform. An iodoform is a bright yellow solid. So if you have a methyl ketone present, you get iodoform formed. But if you have just two hydrogens or one hydrogen on the carbon, notice the reaction will not give you iodoform. So iodoform test is a perfect test for a methyl ketone. Now, one other thing that we've talked about slightly earlier in one of the chapters is that the halogens are also good oxidizing agents. So you can take a halogen and treat an alcohol with that halogen. It oxidizes the alcohol up to a ketone. And then the ketone continues to get reacted in an alpha substitution reaction. So not only is this reaction positive for ketones, it's positive for secondary alcohols. Notice the secondary alcohol gives the same reaction because it's first oxidized to the ketone, and then it can undergo whatever reaction that it undergoes. So let's sum up this statement. If you have a halogen being reacted in a basic solution, it's going to polyhalogenate. It's going to replace all the hydrogens. And if it replaces all three of them, the reaction goes further to form the haloform and the unprotonated form of the carboxylic acid. But what happens if you do the reaction in acidic solution? Oftentimes we use the halogen in acetic acid as a solvent. Notice if we use the acetic acid as the solvent for this reaction, it's no longer in basic solution, it's in acidic solution. So acidic reactions stop at the monohalogenation reaction if you only add one equivalent of the halogen. Now you can force it to add two equivalents of the halogen by adding, you can force it to add two halogens to the alpha position by adding two equivalents of the halogen, but you don't have to. You can stop this reaction at the monoalkylation stage, okay, or the monohalogenation stage, excuse me. So if we take a ketone, even though it's got three hydrogens on it, and react it with a halogen in the presence of acetic acid, notice that we can stop the reaction with monohalogenation. We cannot do that in the basic solution. And the reason is because the compound here is more reactive than the compound that's produced in the first step, okay? And you can read the textbook to see why that is. So that's an introduction to halogenation reactions. So we can replace all the hydrogens by doing the reaction in basic solution, or we can replace only one of the hydrogens by doing the reaction in acidic solution. And we can use either OH- as our base, or we can use LDA as our base.